In this lecture, we're going to discuss optimization problems. These are problems where you're trying to make some function as large or as small as possible. And actually, you've seen some simple examples of this. Back in the section on mins and maxes, you looked at problems like, say, f of x is some function, maybe x cubed minus 4x squared plus 15, and you wanted to find the absolute max and min on some closed interval. So we saw how to do that in the max-min section. But now we're going to look at problems that are a little bit more involved than just that. And maybe let me just lead with an example. So let's say we want to find the absolute maximum and minimum of the function x times y if we also want 2x plus 3y equal to 30 with x and y both greater than or equal to 0. Now offhand this looks pretty different because we have two variables. It's not just a single variable function of x, but I have a function of x and y that I want to make as big as possible and as small as possible. And then I have this extra condition here that x and y have to be related by this equation and that I want x and y to both be positive. So I'm going to set down some terminology that we'll be using in all of these examples. The function that you're trying to maximize or minimize is our objective function. And the equation that relates x and y, the fact that I want 2x plus 3y equals 30, that's a constraint. Right? It's sort of constraining our choice of x and y. Okay, so how do we do a problem like this? Well, our goal is going to be to somehow turn this problem into a single variable calculus problem. So how can we do that? How can we turn this into a single variable problem? Well, the secret is in the constraint right here. If I want 2x plus 3y to be 30, that means that x and y aren't really independent. In fact, I could take that equation and solve it for y. So 3y is 30 minus 2x, and dividing by 3 on both sides, we get that y is 10 minus 2/3 of x. So now let's go put this into the objective. So now instead of x times y, it's x times 10 minus 2/3 of x. So in other words, it's 10x minus 2/3 x squared. So maybe now I'll go ahead and call that f of x. And so the problem now has become to find the absolute max and minimum of this function f of x. So it's starting to look a little bit more like this first problem. Well, the difference is that this first problem, though, had an interval. It had a range of x values to consider. So what do I have here? Well, I said that I want x to be greater than or equal to 0. So that means that the interval that I'm looking at must start with x equals 0. But now, how big could x possibly be? Are there any restrictions? Well, it turns out that there are, because we also want y to be positive. So what happens is that if x is something really big, for example, if x were 1,000, well then y would be 10 minus 2/3 of 1,000, which would force y to be negative. So from the fact that y is positive, that means that 10 minus 2/3 of x is positive. So that means that 2/3 of x is less than or equal to 10. and then multiplying both sides by 3/2, you get that x is less than or equal to 15. Okay, so we want to find the absolute maximum and minimum of 10x minus 2/3 x squared on the interval from 0 to 15. And so now we do what we did before. We find the critical points. So f prime is 10 minus 4/3 of x. Set that to 0 and solve. So 10 equals 4/3 of x. That means that x is 3/4 of 10, so 7.5. And then remember, we just build a table that has the endpoints, so 0 and 15, and then any of the critical points that we find, so in this case 7.5. We plug them all into f of x, which remember is this function right here. Well, plugging 0 in gets you 0. And in fact, it turns out that plugging 15 in also gets you 0. And what do we get for plugging in 7.5? Let me just put that into a calculator. Okay, we end up getting 37.5. Okay, so evidently the maximum value of x times y, subject to the constraints that we had, is 37.5, and the minimum value is 0. Okay, so this is a strategy then that we can use to transform an optimization problem with a constraint and an objective into a single variable calculus problem. And we'll be looking at several more examples of these in the coming lectures.